In the last video, we constructed a confidence interval for a population proportion. Remember that proportions are used when you're dealing with qualitative data. In this video, we're going to learn how to identify the appropriate sample size to develop or to gain a desired degree of accuracy. So before we get started, what I want to do is just review the work we did in the last video. In that last video, we looked at an election example. A polling organization was seeking to determine the proportion of all likely voters are going to vote for issue 5, whatever that is. I don't know. They collected some what they called pre-poll data, pilot data, if you will. 168 likely voters were selected. 186 of those intended to vote for issue 5. What we determined was from that the sample proportion was p hat, which is right here. P hat is 86 out of 168, or 0.512. And excuse me, I'm going to bring my pen up. And for 95% confidence, the Z confidence value is 1.96. So the appropriate calculations, just plug the values in. P hat being our sample proportion, 0.512, 1.96. So this is the formula we'll be using. Remember, this is our Z confidence right here. We got a bottom limit of 0.436 when we plug these values in, and being again the sample size 168. We got a top limit of 0.5888. So interpreting it, which you have to do, we are 95% confident that the proportion of all likely voters that will vote for issue 5 is between 0.436 or 43.6% and 0.588 or 58.8%. Okay. We then, in our example, we said, is it valid? You always have to check validity. We do have a random sample of likely voters for a confidence interval, n times p hat, which is right here. So let me get my pen back. There we go. N times p hat is 168 times 0.512, and that's greater than 10. N times 1 minus p hat. Sorry about that. What I did was I crossed the other out. There we go. Let's get a couple of those away. N times 1 minus p hat, which is right there, is 168 times 1 minus 0.512. That's 81.98. Both bigger than 10. So our confidence interval procedure is valid. All right. Now, let's take a look back at that. Our formula for a confidence interval for a proportion is p hat minus the Z confidence value times the square root, which is the standard error, the standard deviation of our p hats, which is the square root of p hat times 1 minus p hat over n. In this formula, this portion of the formula, sorry, let me get my pen back. This portion of the formula is called the margin of error. Okay, so that is the margin of error. And I'm going to abbreviate that with an E. Okay, so we have start at p hat and go down, subtract in margin of error. Start at p hat and go up a margin of error. So in this case, when I look back at the example I just did previously, 0.512, when you do all of these calculations, you get 0.076. So this is my margin of error. And you, again, start at 0.512 and go up 0.076. So what this leads us to conclude is that with a sample size of 168, the margin of error, which is essentially the accuracy of our confidence interval, is 0.076, or 7.6%. Okay, in the newspaper, when you hear so and so, we think 58% of voters approve of this person with a margin of error of plus or minus 3%. That means it would be, say, 58 minus 3%, 58 plus 3%, or so 55% to 61%. So the margin of error is your level of accuracy. All right, now, so if what we want to do, if looking back at the previous example, we had a margin of error of 7.6%. What if we wanted to be more accurate? Of course, you want to try to be more accurate. So what do? To be more accurate, the first thing you do is you determine how accurate do you want to be. Doesn't that make sense? In other words, you choose your margin of error first. So let's look at the formula. Supposing I choose my margin of error, call it E. And remember, this is the margin of error from the formula. What I'm going to do is I'm going to say let my margin of error, it might be 3% or 2%, however accurate I want to be, and set that equal to this formula. And then what I'm going to do is I'm going to solve that formula for n. And that will determine the appropriate sample size. Doing a little algebra, the first thing I'm going to do is I'm going to divide by my z confidence value. Then I'm going to get rid of my square root by squaring. When you do all of the math, and this is all of the algebra from there to there, you get that n, which is the appropriate sample size, is the z confidence value divided by the margin of error times p hat 1 minus p hat. So that is going to be our sample size formula. Okay, now you might notice, as I'm going to the next slide, you might notice a small problem with that. In this sample size formula, notice that to calculate n, to determine what the appropriate sample size is, which is right here, we have to know p hat. Now again, that's a bit of a paradox. To find the appropriate sample size, you have to have a sample proportion which is drawn from a sample. So how can you, that's the quandary. How do you determine the appropriate sample size if you need a sample to determine the appropriate sample size? Okay, I'm just going to shake my head on that. So in other words, note that a sample proportion is needed to determine the appropriate sample size. Now, how do you get out of that dilemma? There's two ways. The first way is you use a best guess. And that best guess may be drawn from old samples. It may be a sort of a gut feeling, or it might be drawn from pilot data. Okay, so you could use a best guess and plug that in for p hat and calculate your n, calculate your sample size. Or, and this is called the conservative approach. Conservative meaning we're just being safest, if you will. It turns out that p hat times 1 minus p hat is the largest when p hat is 0.5. So if you don't have any other information, you really have no gut feeling about p hat or the proportion, or you don't have any pilot data, what you do is you use 0.5 for p hat. So I'm going to do two examples of these calculations. The first one, and they're both similar to the last example. We're going to look at our likely voters, our proportion of likely voters that intend to vote for issue 5. To estimate that, the organization, if you look back at the original problem, conducts a pre-poll pilot. So in other words, they're going to sort of try to get a sense of how many individuals are they going to need, and in total. So they said, let's get a small sample and get some sense of what's happening here. So how many voters will be needed to estimate the proportion of all likely voters that support issue 5 with 95% confidence? So our formula is n equals, and I also like you to give me the formula in this case, n equals z confidence over e, the margin of error squared, p hat. We have some indication, sort of pilot data. Our p hat is going to be, in this case, 0.512. We're considering that initial data just pilot data. And note, for 95% confidence, the z confidence value, how many standard deviations you need to go up and down to capture the 95% of the data. It's 1.96. So when we plug all that in, we would get n equals z confidence, which is 1.96, divided by the margin of error. You have to use the decimal form, so 0.03. That's an awful 3, sorry. And we have to square that times our p hat, which is 0.512, times 1 minus p hat, which is 1 minus 0.512. I am stylus impaired today, it seems. All right, when you do that math, it turns out that that n, when you figure all that up, I've got it here on a box. So let me get my box. 1,066.496. Now, what does that say? See, we need 1,066.496 people in order to have a margin of error of 0.03. Now, you might say, I'm okay with 1,066. What do I do with that 0.496 of a person? When you're estimating sample size, you always round up. Okay? So what we want to do, if we want to basically estimate the proportion of likely voters with a margin of error of 3%, always round up, we would select 1,067 voters, likely voters, excuse me, are needed in our sample, and that would give us a margin of error of 3%. Our second example is very similar. Let me go to that one. And in this case, it's sort of a different case. Assume we have no pre-pilot data. We just say, how many likely voters do we need to be selected to estimate the proportion of all likely voters that support this issue with 95% confidence, margin of error of 3%. All right. In that case, what you've got is, since there's no other information that you have, your P, we're going to use our P hat rather, okay, we're going to say we don't have any information, so we're going to say P hat is 0.5. We're just going to be basically kind of be cautious, be as cautious as we can be. So in that case, our N would equal, again, our Z confidence is 1.96 divided by our margin of error, 0.03. Remember to square that. That's one thing that people do wrong. Times P hat, which is 0.5, times 1 minus P hat, 1 minus 0.5. And that, when you do all the math, is equal to, let me look over at my box again, 1,067.11. Okay, 1,067, but what do we do with that 0.11 of a person? Again, we always round up, because 1,067.11 gives us an exact margin of error of 3%. We want to be within that. So if we go down, it's actually going to make our margin of error get a little bigger. So you always round up. So what we need to do here is just select 1,068 likely voters.